In this video, I'm going to talk about Taylor remainder formula. So before I get into what that is, I forgot to mention at the end of the last video, when we were talking about alternating series error, that we were done and we had sort of checked off one of our learning goals, which was how we find an upper bound for error using alternating series error. Okay, so sometimes at the end of videos I forget to do this. I'll try my best to remember these, but hopefully whenever I get done with one of these, I'll do my best to remember to go to here and check these off. Okay, so let's get into the Taylor remainder formula now. All right, so I want to begin by stating what's called Taylor's theorem. So we can use the mean value theorem from calculus to show that a function f of x equals this long thing on the right-hand side. Okay, so I'm going to start to explain what the pieces here are. So f of x is our original function. Whatever we are finding a Taylor series of, or maybe just finding some Taylor polynomials of to approximate it, f of x is our original function. This f of a plus f prime of a times x minus a over 1 factorial plus dot 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 plus this nth derivative evaluated at a times x minus a to the n over n factorial. That whole thing, that's Pn of x. That's our nth order or nth degree Taylor polynomial for f. So that is our approximation. That is what we're going to use to approximate that original function. And when we approximate the original function, it's not going to be perfect. It's going to be off, usually by a little bit, and that's what Rn of x represents. This is called the remainder. Okay, and when we use the mean value theorem, one of the things that it tells us is this remainder, Rn of x equals the following fraction. So it sort of looks like the n plus first term of the Taylor series. The one kind of key difference is this is evaluated at some number c, so we're plugging in c into this n plus first derivative instead of a, where c is some number between x and a inclusive. So this phrasing for some c between x and a inclusive, it sort of matches the wording that we see in mean value theorem. So the key thing that I want you to be able to take away from this theorem is that when we have a function and we use its Taylor polynomials to approximate it, it's going to be off by some value, and that value is the remainder. Okay, so the absolute value of that remainder of Rn of x, if we isolate Rn of x, we would get f of x minus Pn of x, and I'm just writing this whole thing in the absolute values. And this is going to be equal to the absolute. So the original function minus the approximation, that is what the error is. So our goal in this section will be to find an upper bound for the absolute value of the error. In other words, find something that's always going to be larger than the absolute value of the error. Okay, so the key consequence of Taylor's theorem is the Taylor remainder formula. And this will give us an upper bound for error. So the context is when we use the nth order or the nth degree Taylor polynomial, Pn of x, to approximate our original function, f of x, the absolute value of the error is less than or equal to the absolute value, maybe let's put this in a different color, m times x minus a to the n plus 1 over n plus 1 factorial, where this number m is a number such that the absolute value of the n plus first derivative of f evaluated at c, that absolute value is less than or equal to m for all values of c that are between x and a inclusive. So in other words, on whatever interval that we're looking at that's between a and x, inclusive, including those endpoints, m has to be a number that's greater than or equal to the absolute value of this n plus first derivative of f on all values in that interval. Okay, so we have a name for this. So m is what's called an upper bound. It's an upper bound for the absolute value of the n plus first derivative. It's an upper bound for that. All right, so let's look at an example where we start to use this formula to find error, or to approximate the error, to get an upper bound for the error. All right, so this is going to be example 2, and this is continuing the numbering of the examples in the section from the previous video, because in the previous video I did example 1. So part A of this example is use the third Taylor polynomial. And what I mean by third is third order or third degree, third order Taylor polynomial of e to the x that's centered at x equals 0 to approximate e and round to 5 decimal places. So in terms of the Taylor series formula, when it says it's centered at x equals 0, that means that the a value, a represents the center, is 0. Okay, and then I want to round to 5 decimal places. And let's do this for good practice without using the Taylor series formula. In other words, let's go through the steps of how we find the Taylor series formula. Okay, so I want a third order Taylor polynomial. So I want P3 of x, and that's going to look like some constant a0 plus a1 times x, because it's centered at 0. It's not x minus a, it's just x. And then plus a2 times x squared plus a3 times x cubed. And we want to figure out what these coefficients are. Okay, so I got to start with my original function, f of x equals e to the x. And I'm going to have to take the first 3 derivatives of this. So let's take the first derivative, but luckily all the derivatives of this are the same, which is going to make a lot of our computation pretty quick. So even the third derivative is just e to the x. And then I have to plug in whatever we are centering our Taylor series at into all of these. Okay, so when I plug 0 in to this, and when I plug 0 in to the first derivative, and 0 into the second derivative, and also, whoops, one more tick mark, 0 into the third derivative, I just get e to the 0 for all of these, which is 1. So all of those are just 1. So now remembering our formula for the coefficients, the constant coefficient a0 is going to be the original function evaluated at that center point divided by 0 factorial. Well, f of 0, the numerator is 1. 0 factorial is 1. And 1 over 1, that's just 1. Okay, then we keep going. Let's do a1 and a2 and a3. So a1 is going to be the first derivative evaluated at that center point, 0, divided by 1 factorial. So the numerator is 1, and 1 factorial is 1, and that gives us 1. a2 would be, now this is going to be the second derivative evaluated at 0, but now divided by 2 factorial. So plugging 0 into the second derivative, we got 1, so that's the numerator. 2 factorial is 2. Okay, so we just have 1/2 there. And a3 is going to be the third derivative evaluated at 0, divided by 3 factorial. The numerator we just got here, that was 1. And 3 factorial is 6. But just so we can see the pattern better, actually, let me keep the factorial here. 2 factorial, same thing here. I'll keep the factorial. A little bit later, I'll write out what they are. Like the first one is 1 over 2, and 1 over 3 factorial, that's 1 over 6. I'll write that a bit later. Okay, so now that we have those, we are ready to plug in to our polynomial. So P3 of x, well, our constant term coefficient was 1. A1 is also 1, so we'll just get x. The x squared coefficient was 1 over 2 factorial, so we'll get x squared over 2 factorial. Let's write that a little bit better. Kind of looks like 21 right now. 2 factorial. And then the x cubed coefficient is 1 over 3 factorial. All right, so now if I really want to see the pattern on this a little bit more, the x term, we could have put that over 1 factorial. Okay. So then let's use this to approximate e. So if I want to know what e is, remember this all originated from the function e to the x. So with this 1 plus x squared over 2 factorial plus x cubed over 3 factorial, that was a way to approximate e to the x. So I would need to plug in 1 in for the x to get e to the 1. So in other words, e is f of 1. So let's plug in 1 into our Taylor polynomial. And if we do that, we would get 1 plus 1 plus 1 over 2 factorial 1/2 plus 1 over 3 factorial, which is 1/6. Okay, and I'm going to go ahead and use a calculator to put this in decimal form. And the question said to round to 5 decimal places, so I'd get 2.66667. So we approximated e using this third order Taylor polynomial. Next, let's use the remainder formula to get an upper bound for the error. So that's going to be part B precisely. Use the Taylor remainder formula to give an upper bound for the error. So let's remember what the Taylor remainder formula says. It says that the absolute value of the error is going to be less than or equal to the absolute value of m times, so I'm going to give myself a little bit of space to fill stuff in. So typically here, we would have x minus a in the parentheses. But we know that a, the center point, is 0. We know that x, the value that we're actually plugging in to estimate what's going on there, is 1. So we'd have 1 minus 0 here. That would typically be x minus a. And then up here, we'd have the exponent. So the exponent, what goes there is n plus 1. And our value of n here is 3. Because we're using a third order Taylor polynomial. So the exponent would typically be n plus 1. So I'm just going to write, let's erase that actually. Let's give myself a little bit more room. This would be 3 plus 1. And the denominator is a factorial. And specifically, it's n plus 1 factorial. So it would be 3 plus 1 factorial. Okay, so I've just plugged some stuff in to our Taylor remainder formula for the error. So our key goal is now to figure out what m is. So we need to find m. And we do that using, and we had a formula to, on what m is. It's the absolute value, so the absolute value of the n plus first derivative evaluated at c needs to be less than or equal to m. And this has to be true for all values of c that are between a and x. And a, we determined already, was 0. And x, so a was the center point, and x is the value that we're plugging in to estimate what's going on there. That was 1. Okay, and this needs to be true inclusive. So one thing let me do to simplify this a little bit. N I know is 3, which means n plus 1 is going to be a 4 here. We're talking about the fourth derivative evaluated at c. Its absolute value needs to be less than or equal to m. Okay, so to get a feel for what m might be, we need to take the fourth derivative. But because we were just dealing with e to the x, all the derivatives are easy. The fourth derivative is also going to be e to the x. And now let's plug in c into it. Okay, so the absolute value of the fourth derivative evaluated at c is going to be the absolute value of e to the c, because I'm just plugging the c in for the x. So what is this always less than or equal to? Between 0 to 1, inclusive. In other words, I sort of want to know what's the largest this gets. Well, the largest e to the c, the largest this gets on the interval from 0 to 1 is, it happens to occur when c, the exponent, is 1. And when c is 1, we end up with e to the 1, or just e. But the whole point of this problem was to approximate E. So I don't want to use E for M because we're sort of assuming that we don't know what E is exactly. The point is to approximate E, so we can't use E for M. In fact, let me write that out a little bit bigger. We can't write E for M. Okay, so what I'm going to do now is I'm going to be a little bit extra safe. So I'm just going to write something that's even larger than this. What's something that I know for sure is larger than E? Well, I know that 3 for sure is larger than E, because I know E is 2 point something. Okay, so this is what I'm going to choose for M. I'm going to choose this for M. So technically, I can choose anything that's larger than the absolute value of e to the c here. So if I wanted to choose 5, I could have, because that's going to be larger than e is. If I wanted to choose 142, I could have. For our purposes, we want to get usually we want to get the best possible upper bound, the smallest possible upper bound. That's what I mean by that. So when possible, we like to pick maybe the smallest possible thing that we can for m. But we have flexibility there. So if I wanted to choose something slightly larger to be extra cautious, I could, but 3 definitely works. Okay, so let's use this. Let's use this in our formula. So the absolute value of the error is going to be less than or equal to, well, let's put this in black actually, less than or equal to the absolute value. Let me zoom out a little bit so we can see the formula. Less than or equal to, all right, let's write the value of m there in the numerator, which is 3. So 3, and then we'll have 1 to the 4th, so times 1 to the 4th. And the denominator is 4 factorial. So 4 factorial. And that, if we simplify this, is 0.125. So 0.125 is an upper bound for the absolute value of the error. Okay, so now I want to note a key thing. So note that the actual error is the absolute value of the true value, whatever e is, minus the approximation that we got in part A, which was 2.66667. So that's what the actual error is. We are just estimating that actual error. So we can't use this since the point of the problem is to approximate E. So I can't just use E minus 2.66667 because the point of the problem was to figure out what E is, or approximate it. That's why I have to use the Taylor remainder formula here to get this estimate on the error. Okay. All right, so 0.125, that was the answer to part B. We got an upper bound for the error. Let's move on to the next part of this question. So now let's use parts A and B to find an interval that contains the E. Okay, so what we know now is, let's put this in a different color, E is in between two values. It's going to be greater than 2.6667 minus some number, and it's going to be less than 2.66667 plus some number. In other words, I'm sort of taking my estimate that I got, and I'm going to subtract and add a number from it. And the number that I'm going to subtract and add here is this upper bound in the error. It's the 0.125 that we just got, 0.125. We can say for sure that E is going to be somewhere between these two numbers, because this was the most the error could be, the most that our approximation could be off. Okay, so if we simplify these values, we get 2.54167 on this side. On the other side, we get 2.79167. So we get that E is between these two numbers, and this is true. This is okay, but could be better. It's not a great approximation. Could be better. All right, so the last part of this example is going to be, now let's try to refine this a little bit. what if I wanted to find the smallest order Taylor polynomial so that our approximation was off by at most 0.001? Because that would be pretty good if we could get it within 0.001. So what we want here, oh, let me scroll up a little bit, that's a little too far down. So we want to do something with the error. So let's look at the absolute value of the error in our error formula. So the absolute value of the error is less than or equal to the absolute value of. So our value of m isn't going to change no matter what the derivative is. I get to write 3 there. So I get to put 3 here for m since, actually let me just write it this way. It's the same m value since all the derivatives are the same, because we're just talking about e to the x. All the derivatives are e to the x, and 3 is going to be an upper bound for what we had before. Okay, in this next parentheses, we'd have, it's still going to be a 1 in here, because it's the a, it's the x minus the a, and the exponent is going to be n plus 1. Now we don't know what n is. And the denominator is going to be n plus 1 factorial. Okay. Okay, so I'm going to impose something now. So I am going to want something here. Okay, so I just need a little bit more room to write. That's why I scooched that over to the right a little bit. Okay, so I want this to be less than or equal to 0.001. So I'm going to say that I want this absolute value of this fraction to be less than or equal to 0.001, because if that was true, then the error that I have here would be less than or equal to, because I have these two inequalities, would be less than or equal to 0.001, like I want it to be. Okay, so that's important. This 0.001 needs to go on the right-hand side here, not the left. Because if the 0.001 was less than or equal to this fraction, then I don't necessarily know that 0.001 would be greater than the error, like I need it to be. I need 0.001 to be greater than the error. That's why I want to put it here on the right-hand side. Okay, so now let's simplify this. I think I deleted I erased one of my absolute value symbols. Okay, so we got the absolute value. Actually, no. I actually don't need absolute values because everything here is positive. I end up with 3 in the numerator, because 1 to a power is just 1. N plus 1 factorial in the denominator is less than or equal to 0.001 is 1 over 1,000. And if we rearrange this a little bit, this is equivalent to saying that 3,000 is less than or equal to n plus 1 factorial. So I need to know what's sort of the smallest factorial that ends up exceeding 3,000. So we know that 6 factorial, if we work it out, is 720. 7 factorial is 5,040. So having 7 factorial will get it done. Okay, actually, no, I don't want to go down there just yet. So at this point, we are ready to say what the smallest n would be. We would need n plus 1 to be equal to 7. And if n plus 1 needs to be 7, that means that n would have to be 6. And that's our answer there. That's the smallest order we could take, 6th order, so that our approximation would just be off by at most 0.001. Okay, so I want to end this video by getting a feel for, well, how good is this actually? So if we use the 6th order polynomial, and we plug in 1, so let me write that. So now we plug in x equals 1 into it, we would end up getting 1 plus 1 over 1 factorial plus 1 over 2 factorial plus, and I would keep going like that until I get to the 6th order term, so 1 over 6 factorial. The numerators are 1 because I've plugged in 1 into the numerator, in for x, sorry. And if we use a calculator to evaluate this, we end up with we end up getting that this is actually exactly equal to 2.71805 repeated. And just for comparison, the actual value of e, if I just write some more decimal digits of it, is 2.718 281, and then it keeps going. So that's the actual value of E. So this is a pretty good approximation. We're a whole lot closer with this to the actual value of E. Okay, so at this point, we have finished learning goal 1. We have talked about how we find an upper bound for the error using the Taylor remainder formula. In the next video, I want to get some more practice with this, so we'll do another example.